Imagine dangling on a rope, like 42 feet underground,
Yeah.
just totally enveloped in near pitch black darkness.
Oh, yeah, just void.
Right, a total void. And far above you, there's just this single pale shaft of daylight piercing through the forest floor.
Yeah.
And below you, the sound of rushing floodwater is echoing off these slick limestone walls.
Which is terrifying because it's quickly turning the pit you're descending into a violent waterfall.
Exactly. And the crazy thing is, this isn't some remote, highly sponsored expedition in the Andes or something. This is a Tuesday afternoon on a quiet, seemingly ordinary wooded hillside right in the Midwest.
Yeah, I mean, if you were just, walking your dog on the surface, you would literally never even know that subterranean world existed beneath your boots.
You just walk right over it.
Yeah.
So today, for you listening, we're diving into a stack of incredibly detailed geological and survey data from the Indiana Cave Survey, Inc. And this was just recently updated in 2021.
Right, it's very fresh data.
Yeah. And our mission today is to look at one hyper-localized patch of land in Lawrence County, Indiana. It's an area known on the maps as the Bedford West Quadrangle.
Which is such a specific, unassuming name for what's actually there.
It really is. And we are sitting right on the boundary line between private property and the federal Hoosier National Forest. To the naked eye, I mean, this landscape is just a tangle of trees, leaf litter, a few ravines, but underneath it is a vast, complex maze. So, okay, let's unpack this, because we're looking at the raw data of what it takes to actually map the unknown.
And we should probably clarify right up front, we aren't talking about commercial tourist caves here.
Oh, definitely not.
Yeah.
There are no paved walkways here, no colorful floodlights pointing at stalactites, and absolutely no gift shop at the end.
No, what we're examining in these survey sheets is the hard, unfiltered data of human beings squeezing themselves into muddy fractures in the earth. I mean, they are often putting themselves in extreme danger simply to figure out where the water goes.
It's wild. And to understand the sheer difficulty of this kind of mapping, we kind of need to start with the smallest data points, right? Because finding the entrances to these systems isn't like stumbling across a giant, gaping cavern on the side of a mountain.
Not at all. It's much more subtle.
Yeah. Let's look at the data for a site known as Big Cave. It's designated as LA-174 in the survey. The database shows it was discovered by a caver named Harold Geik. It's 50 feet long and about 26 feet deep. But what really gets me about Big Cave is the scale of the entrance.
Oh, the 2004 field notes by Surveyor B. Trotter are incredibly specific about this. Big Cave is located on a gently sloping, north-facing hillside.
But the entrance is just a tiny depression in the ground. It's like 3 feet deep by 8 feet across.
Basically the size of a large bathtub.
Right. So in a dense forest full of leaves and uneven terrain, how does a surveyor even spot that without accidentally just tripping right into it?
Honestly, it's a valid question.
Trotter's notes explicitly warn future cavers, and I'm quoting here, you have to be on top of it to locate it. It requires a vertical climb down, and the survey very politely suggests that a, quote, hand line may be nice.
May be nice. Gotta love the understatement.
Right, which feels like a profound understatement for lowering yourself into a jagged limestone crack.
Yeah, a hand line is the absolute minimum requirement there. But finding something like Big Cave, it really requires a fundamental shift in how you read a landscape.
What do you mean?
Well, surveyors aren't just wandering aimlessly through the woods hoping to fall into a hole. They are reading the topography for anomalies. So a small 3-foot depression on a slope means the soil is subsiding into a void below.
So the dirt is essentially falling into the roof of the cave.
Exactly. And just down the hill from Big Cave, on the same property map, there's another site called William Cave, or LA-220.
Oh, yeah. Discovered in May of 1980 by Dave Black and Dave Doolin.
Right. And this one is a bit more substantial at 264 feet long and 19 feet deep.
The notes clarify it's located in a sinkhole at the end of a ravine, and it requires an 11-foot climb down. They also, they strictly clarified this is not a site called Real Cave, which is apparently further down the hill.
Which is just classic, highly literal caver humor. Gotta love it.
But the crucial detail for William Cave, and the reason we're bringing it up, is that the notes say water flows directly into the entrance.
Yes. And that flowing water is the key to everything in this data set. I mean, to a geologist or a dedicated surveyor, there's no such thing as an isolated hole in the ground in this region.
Because the notes keep mentioning St. Louis limestone. Right. Which immediately signals we are dealing with karst topography.
Precisely.
So we aren't just talking about solid rock cracking from an earthquake or a tectonic shift. We're talking about a slow-motion chemical reaction where water is actively dissolving the ground beneath our feet.
And what's fascinating here is the specific mechanism of that dissolution.
Yeah.
Like as rainwater falls through the atmosphere and percolates down through the soil, it actually picks up carbon dioxide.
Yeah.
And this creates a weak carbonic acid. So when that slightly acidic water hits the calcium carbonate of the St. Louis limestone, it chemically eats away at the rock.
It literally dissolves it.
Literally. And we are talking about a process that takes tens of thousands of years. It exploits the tiniest horizontal bedding planes and vertical fractures in the rock. So over millennia, a microscopic fracture becomes a crack becomes a fissure, and a fissure becomes a cave.
Wow. Which totally explains why even bother mapping a tiny 50-foot crack like Bit Cave or a sinkhole like William Cave? It's so vital.
They aren't just random pits.
Right. They are the intake valves for a massive subterranean drainage system.
Exactly. Every puddle that drains into the rock, every stream that vanishes into a ravine, it's a critical data point.
Yeah.
Hydrologists need these maps to understand the regional plumbing.
Because that water that enters William Cave might travel for miles underground, right?
Oh, easily. And it eventually resurfaces at a spring that might feed a local water supply. So if you don't map the intake, you really can't protect the output.
But all that water draining into William Cave, it has to go somewhere locally first. The limestone bedrock here essentially acts like a funnel, routing these tiny tributaries into massive main arteries.
Yes, it compounds.
And if you follow the topography down the ravine on this specific Bloomer property map, you don't just find another crack. You find the drain for the whole system, which is HNF Swallow Hole, officially designated LA010.
The letters HNF standing for Hoosier National Forest, of course.
Right. And this site is an absolute monster compared to the other two. It is 1,844 feet long and 89 feet deep.
It's massive.
Instead of a little depression in the leaves, this cave opens with that huge 42-foot pit right in the middle of the ravine. And I love this. The survey data shows it has some colorful aliases documented all the way back in a 1961 guidebook by R. Powell.
Oh, the aliases are great.
They specifically refer to it as Betty Barf's Pit and Betty Don't Care Pit.
Yeah, and those names, they usually stem from an inside joke on the initial expedition. It's very often related to the miserable conditions someone endured during the survey.
I can only imagine what Betty went through down there. But the data shows this massive system wasn't mapped in a single weekend. The initial survey began with D. Black in 1976, but they didn't even find the end of it.
No, it kept going.
Right. Later, a caver named Jeff Forbes pushed much further into the system, and what he found sounds intensely claustrophobic. The notes indicate Forbes discovered an 800-foot crawl space, which eventually led to 2 offset 20-foot pits.
Just think about the physical reality of that. To map something like that, you are dragging yourself through cold mud on your stomach in a passage that might only be a foot or two high.
800 feet.
Right. You are doing this for the equivalent of almost 3 football fields, and you're dragging your survey tape, your compass, and your lighting gear the whole time.
That's basically 2.5 football fields of solid rock, just inches from your face. With no guarantee that the passage even opens up at the end, that requires a very, very specific type of psychological endurance.
It's definitely not for everyone.
But here's where the data set for HNF Swallow Hole gets incredibly technical, and where I actually have to question the process a bit.
Okay, let's hear it.
There's a note from 2021 by surveyor Kay Dunlap about updating the cave's GPS coordinates in the master database. The old coordinates were derived from a report by Dave Everton, but apparently the conversion to latitude and longitude was somehow off.
Yeah, data migration issues are actually incredibly common in these decades-spanning longitudinal surveys.
I get that.
Yeah.
So Dunlap went into the archives, pulled 2 separate raw GPS readings, one from Brian Killingbeck and one from Everton, and he averaged them out. But the note specifically says those 2 historical readings were only 44 feet apart.
Right.
My phone's GPS routinely drifts by 44 feet while I'm just sitting at a stoplight. So in a dense, overgrown, 3-dimensional forest, why go through the bureaucratic math of averaging historical data over a margin of error that small? Does a margin of error that small really matter?
If we connect this to the bigger picture, that 44-foot discrepancy is everything. Absolutely. First, let's talk about the physical limitations of the technology itself. You mentioned your phone, GPS. In a dense Midwestern forest, especially when the canopy is wet from rain, satellite signals are heavily degraded.
Oh, sure.
Getting a pure reading is notoriously difficult. But the real issue is how subterranean maps actually work in relation to the surface.
Right, because GPS doesn't work underground at all.
Exactly. GPS cannot penetrate solid limestone. So when Jeff Forbes or D. Black were mapping those 1,844 feet of H&F swallow hole, they were using traditional line-of-sight surveying.
Which is what, exactly?
Compass bearings, inclination angles, and tape measures. They painstakingly build a highly accurate three-dimensional geometric model of the cave underground. But that entire subterranean model has to be digitally pinned to the surface of the Earth at the single entrance point.
Oh, wow. Wait, I see where this is going. If the pin on the surface is in the wrong place, the whole map underneath it shifts.
Precisely. If your surface entrance coordinate is off by 44 feet, your entire digital map of the cave is floating 44 feet away from reality.
That's crazy.
You might look at the map and think a passage runs safely under a public forest, but due to that surface error, the passage is actually running underneath a state highway or, someone's private foundation.
Which brings us directly to the human boundaries shown on these survey sheets. The maps clearly show the bright red lines of property borders. These caves sit right on the boundary line between private land owned by Deborah and Robert Bloomer, according to the 2021 data, and the federal Hoosier National Forest.
Yeah, and from a legal and ethical standpoint, 44 feet is the difference between exploring public land and literally trespassing in someone's private backyard.
That's a huge deal.
It is. The note by Dunlap mentions that the previous inaccurate location suggested the cave was entirely on an adjacent property. So getting the coordinates mathematically perfect is essential for maintaining the integrity of the survey and respecting those landowner rights.
Makes total sense. And understanding the exact location of that entrance pit brings us to the gritty physical reality of what happens when human beings actually interact with this specific landscape.
It's not a sterile environment.
No, the survey sheet for H&F Swallow Hole has a dedicated field for hazards, and it bluntly states just a few words: entrance pit floods are. And reading through the historical trip reports gives you a terrifying picture of what that actually implies.
The hydrology in karst regions is highly dynamic. When it rains, the landscape changes character entirely. It can happen fast.
In 1987, a surveyor named S. Collins filed a report stating that on their trip, only the entrance pit was explored. And the reason? There was a massive debris choke in the crawl leading from the pit.
Yeah, that happens a lot.
The passage was completely clogged with flood debris. To use kind of a municipal plumbing metaphor, if William Cave is a small street grate, H&F Swallow Hole is the main storm sewer.
That's a really good way to visualize it.
Most of the time, the water is just a trickle. But during a heavy rainstorm, that entire drainage basin funnels down the ravine. And that 42-foot pit essentially becomes a high-pressure intake pipe.
And that hydraulic pressure forces branches, mud, rocks, and leaves deep into the cave system. It violently rams them into those tight crawl spaces until they form an impenetrable plug.
Wow.
Yeah, S. Collins encountered the aftermath of one of those floods.
The visual data attached to the survey really reinforces how intense this environment is, too. The photos show cavers dangling on ropes down these massive, layered limestone pits, with the rock walls heavily streaked and scoured by centuries of rushing water.
You can clearly see the water damage.
You really can. And the photos from deeper inside show those low, tight stream bed crawls. You can see the water pool on the floor, the thick, heavy mud coating, absolutely everything. Yet in the upper, drier rooms, the ceilings are dotted with incredibly delicate, beautiful stalactites.
It's an environment completely defined by extremes. It can be incredibly pristine, but it is deeply unforgiving if you misjudge the weather on the circus.
So what does this all mean for you and me, or, for the surveyors themselves? Like, why does knowing about a debris choke from 1987 matter to someone exploring the cave today in 2024?
Well, this raises an important question about the ethos of the Indiana Cave Survey and just cave exploration in general. It is not some individualistic, adrenaline junkie pursuit.
It's not just thrill-seeking.
Not at all. It is a highly disciplined, community-driven effort that relies entirely on shared intelligence.
It's essentially an open-source survival guide.
Yes, beautifully said. The meticulous mapping, the tracking of coordinates down to the single foot, the historical documentation of flood chokes. This knowledge isn't academic. It is highly practical information that dictates whether you rig a rope differently or whether you cancel a trip entirely just because there's a 30% chance of rain.
Right.
Furthermore, this community survival relies heavily on a social contract with the landowners themselves.
Oh, the survey notes provide a really great historical example of exactly that. There is a note regarding the previous landowners, the Bridges family. It states they would allow cavers to explore H&F Swallow Hole and a neighboring system called Fuzzy Hole, provided the cavers followed some strict rules.
You had to check in, right?
Yep, they had to ask for permission before going underground, and they had to notify the family the moment they safely made it out.
The landowners were acting as a critical safety net. I mean, they lived on the land. They knew exactly how quickly that ravine flooded.
Because they see it every time it rains.
Exactly. So if a team of surveyors didn't check back in by a certain time, the landowners knew to initiate a rescue. It demonstrates a deep mutual respect for the hazards of the natural world. The cavers respect the landowner's property, and the landowners respect the inherent danger the cavers are facing just to collect this data.
Let's take a step back and look at the trajectory of the data we've been unpacking today. We started on a quiet, seemingly ordinary wooded hillside in Lawrence County, Indiana. We looked at Bit Cave, this elusive 3-foot depression hidden in the leaf litter, requiring a surveyor to practically stand on top of it just to notice a 26-foot drop into the dark.
A vital clue in reading the subsiding landscape.
We looked at William Cave, acting as a small intake valve for the water flowing down the ravine, and then we followed that water all the way to the massive 42-foot pit of H&F Swallow Hole.
Where cavers push through an 800-foot mud-filled crawl space just to map a tiny fraction of the subterranean plumbing?
It's incredible. We've seen how vital it is to digitally anchor that map to the surface down to the foot, navigating both the technical limits of GPS in a dense forest and the legal lines of the Bloomer property map.
It is a profound testament to the human desire to understand our physical environment, no matter how harsh or hidden it is.
It really is. And for you listening, it should profoundly change how you look at the landscape around you. Whether you are walking through a state park or just looking out at a forested hill behind your own neighborhood, it really makes you wonder what unseen geological wonders might be hidden just beneath the soil.
Just waiting there.
Yeah, just a few feet of dirt and limestone separating our normal sunlit world from an ancient, silent labyrinth waiting to be mapped.
Because the surface topography we see every day is really just the roof of a much more complex structure.
Exactly. But before we wrap up this deep dive, there is one final, lingering idea drawn from these survey sources that completely reframes everything we've just analyzed.
Oh, what's that?
Well, we've been looking at these maps. D. Black's initial survey from 1976, Jeff Forbes' 800-foot edition, Key Dunlap's 2021 coordinate updates. We tend to treat maps as static documents, a final statement of what exists.
But karst topography is never static.
Exactly. The source text repeatedly mentions water. Water actively flows into William Cave. The entrance pit to H&F Swallow Hole acts as a storm drain that violently floods. Water combined with carbon dioxide is the active chemical mechanism that carved the St. Louis limestone in the first place.
It's an ongoing process.
Right, which means the maps created by these surveyors aren't final at all. They are merely snapshots in geologic time. As we speak right now, water is still flowing down those ravines. It is still slowly eating away at the microscopic fractures in the rock.
That's a great point.
Thousands of years from now, could the flowing water eventually eat through the remaining limestone walls, separating these adjacent systems? Could Big Cave, William Cave, and the massive H&F Swallow Hole eventually dissolve into one another, connecting into one colossal unified supercave?
The plumbing just getting bigger and bigger.
We think we've mapped the unknown. But the truth is, the map is never truly finished. The Earth is just busy drawing the next draft.